All right, good afternoon, everybody. How's everybody doing this afternoon? Welcome, welcome. We're very, very glad that you're here. My name is Nathan Johnson. I'm a psychology instructor here at Wayne Community College. We want to welcome everyone to our gallery opening for the Snapshot Climate Change Photo Exhibit. This exhibit, which is out in the atrium, and the gallery opening are part of Wayne Community College's Spring 2025 Arts and Humanities series. With support from the North Caroliniana Society, Wayne Community College has partnered with Southern Cultures and UNC's Carolina Public Humanities to sponsor this event. The photo gallery that's displayed in the atrium that you guys all walked through is from the fall 2023 issue from the journal Southern Cultures. These photos and their accompanying essays highlight the many ways in which climate change is affecting the southeastern United States. In addition to that, Wayne Community College hosted a photo contest in which entrants submitted photos documenting the effects of global climate change in Wayne County and worldwide. The winning entries for this contest are displayed here in front of the stage. Today we are very fortunate to have an amazing speaker who will explain the importance of this photo gallery to us. Dr. James W.C. White is the Craver Family Dean from the College of Arts and Sciences at the UNC-Chapel Hill, which is the largest school from our nation's oldest public university. The College of Arts and Science is the university's third largest research enterprise, bringing in more than $140 million in research funding a year. He's an internationally recognized expert in climate science and has published some 200 peer-reviewed journal articles. He is highly cited and regularly gives public talks on climate change and sustainability. Please join me in welcoming Dr. James W.C. White.
I have to start with a little bit of water here. I don't know if y'all noticed, but there's a little bit of pollen out there in the air. It's a little yellow. It was like a yellow snowstorm driving in here. I am going to wander through, well, there's a lot we could talk about. I've long taught a course on climate change, and it takes 16 weeks to go through at least just the basics. So in the next 40 minutes, we're not going to get through a whole lot. But let's, hopefully we can get you through some, I think through some basics and through some, hopefully some challenges. I want you to look at and think about climate change in a different way. And I want this thing to go forward or backwards. Okay, so setting the stage. So it's important to recognize that we humans are the major agent of change on the planet. Right? We move 10 times more dirt than all natural erosive processes. And what I mean by natural erosive processes is that when continents slam into each other and mountains are raised up, or when one tectonic plate goes underneath another and mountains are raised up, then the rain falls and the snow falls and the mountains begin to erode and the rivers carry the sediments. So over the entire globe, that process is going on a massive scale. And we come in with our Caterpillar tractors and everything else, and we move 10 times more dirt than all natural erosive processes. So that's one way to think about this. Another is to think about it in terms of nitrogen fertilizer. So nitrogen, you want to grow plants, you're going to need nitrogen, phosphorus, and ammonia. All right? And ammonia is the nitrogen fertilizer. We exist on this planet because of photosynthesis. Photosynthesis produces oxygen and sugars, and it allows us to exist. It's a nice symbiotic relationship. We eat plants, and then we won't go into that. Anyway, in order for plants to be out there, plants need nitrogen fertilizer. Now, how do they get nitrogen fertilizer? Nitrogen fertilizer comes from bacteria that live in the soil that take nitrogen from the atmosphere, N2, which is not, it's an inert gas. I'm waving it around right now. It's 70% of what's in the atmosphere. They take nitrogen gas, which we cannot use, which plants cannot use, and they convert it into a form which is soluble in water so the plant can take it up through the roots and use it in photosynthesis. Now, why is nitrogen important? Nitrogen is a key element in making amino acids, and amino acids are just the structure, the protein structure of what's in plants and also in us. I can't begin to tell you how many bacteria are out there taking nitrogen out of the atmosphere and making it into ammonia. We figured out how to take nitrogen out of the atmosphere and make it into fertilizer in the 1930s. The Haber-Bosch process. People got a Nobel Prize for that. So basically in one generation on this planet, we went from not being involved at all in the nitrogen cycle to today where we make more nitrogen fertilizer than all those bacteria on land. And again, I would challenge you to wrap your head around the fact that there's a lot of bacteria out there working away doing this. There are many other ways in which we can show this. We use many resources, and I won't go through that. I will tell you that, for example, fresh water on the planet falls as rain, rivers flow, there's groundwater. We use all the fresh water on the planet. Now the good news about fresh water is it recycles. I don't need to go into detail about how that works, but you recycle all the water. You recycle water all the time. That goes back into the water treatment plant, goes back into the system, and that water gets used over and over again. Today, if you just add up all the fresh water that we use on the planet and all the water that falls from the sky, they're about equal. So that gives you another way you can scale the size of human beings. We use many resources faster than they're created. All right? And that's a problem. So fossil fuels are one, we'll talk about those today, but phosphorus is another one. So the phosphorus that's used in fertilizer, we use that faster than it's being concentrated by natural processes on the planet. So at some point we're going to have to pay a phosphorus bill on this planet, and that day's not here yet, but it's unfortunately on its way. Okay. All right. All basic global needs, energy, food, water, shelter, etc., have environmental impacts. So when I first started to lecture about climate change in public and sustainability in public about 25 years ago, I would get a question a lot, can we live on this planet sustainably, or can we live without having an impact on this planet? And the answer is no, we can't. There's too many of us. We live too well, frankly, to do that. Now, that's not a bad thing, but it is just a thing, right? We're no longer at the point where we are passengers on planet Earth as it spins through space. We're in the driver's seat, okay? And that's an important change. Arguing about how we manage those impacts is nothing new, right? So one of the things that I want you to recognize that climate change is only one of many, many, many arguments that we've had throughout human history about the impacts of humans on the environment. So tetraethyl lead was in gasoline. It was taken out in the 1960s. All right, but for an entire generation or so, 40 years or so, lead was in gasoline. It took us about 40 years to get that out. Smog, mercury, perchloroethylene, which is dry cleaning fluid. Cigarettes, we knew cigarettes were bad for us long before they put a warning on the package, okay? And that's just how we work as human beings. We know, the experts tell us there's a problem, and we listen to the experts, and then people come in and they've got a vested interest and they don't want us to change, and we argue and we go back and forth. And eventually the evidence piles up so high and so deep that we go, okay, we got to do something about this. We'll put warning on a pack of cigarettes, all right? Lead is an interesting example. So when automobiles were first invented and oil was pumped out of the ground, we converted that to gasoline. The engines knocked and pinged, and so we needed something in there to help with the oxidizing process, and tetraethyl lead was one of the, oh, I knew this was going to happen. Tetraethyl lead was one of the compounds that we put in there. The early epidemiologists, people who study the impact of diseases on humans, raised their hands and said, this is a remarkably bad idea. It's remarkably bad because what you're going to do is you're going to take lead out of the ground, you're going to turn it into lead in the atmosphere, and at the time, most of the cars were driven in cities. So the problem was that all the kids who lived in the cities were going to get dosed with lead. Now, lead causes, slows brain development, causes behavioral problems, and at the bottom here is what I call a good argument starter. What you see here is the amount of lead in blood and the juvenile property crime rate lagged by about 17 years, or the time it takes for us to grow up. Right? So this is correlation, but it's, as we study this, as we understand this over time, it's becoming more and more clear that we basically dosed an entire generation, particularly of inner city kids, with lead. And that led to not only juvenile property crime, but it also led to violent, probably violent crime as well. Right? So this is an example of, yes, we know there's a problem, we should do something about it, we really don't do anything about it for a while. It just takes a while. So I don't want you to think that climate change is something new and unique along those lines. There's many times where this has happened. By the way, it's a good argument starter because I used to my students would go home over Thanksgiving break. I taught a course on environmental issues, and they would come back and they would tell me the absolute disaster that occurred during Thanksgiving dinner when, you know, Uncle Fred launched into this discussion about climate change, and they would say, well, we've been learning this in class, and, you know, I would listen to them, and I'd say, you know what, you need something else to talk about, right? So I gave them lead and gasoline as an alternative to talk about. How'd we get here? Two simple reasons. Number one, there's a lot of us, and by the way, the power of the exponential is really remarkable, right? So if you go back 10,000 years ago, right in here, 8 to 10,000 years ago, the Sphinx and the pyramids. So we've been around, we're here. And then somewhere around 1 AD, we started to kick in, and then it just takes off. That's the power of the exponential. Right? So in a pretty short period of time, a lot of us showed up on the planet. In my lifetime, the population has gone up by billions. The other thing that has changed is that in order for us to have the lifestyle that we have, we need a lot of resources. This is a plot of energy use in tons of oil equivalent per capita versus the GDP per capita. So in order for us to live in the United States here, Australia, Canada, et cetera, even Germany, Italy, we need a lot more resources than they do in India, Brazil, China, et cetera, to live their lifestyle. Now, it's important to recognize that as this goes up, this is actually the big multiplier. Yes, there's a lot of us, but if it takes 3 times more energy per person to have the lifestyle that we have over what they have in China, imagine what happens when China industrializes to the point where they are also using energy at the same rate that we are. That's the big multiplier. That's the one that, as climate scientists go, and as energy scientists, that's the one that we are focused on and the one that we not worry about, but one we're concerned about. The dot size here is the size of the population. So when India and China in particular move up this graph, then you see a lot more energy being consumed. And if that energy is fossil fuels, you see a lot more carbon dioxide going to the atmosphere. Okay. Fundamental question. Can humans live sustainably on our planet? All right. I asked that question because of what I'm looking at here. Sustainability is inherently an issue of humans and the environment. Right? It's about us. It's about our sustainability. Right? That's important to recognize. And while it sounds egotistical, we are. Right? So that's what we want to do. The environment on our planet operates on physical and chemical principles that are they're fixed, unbreakable laws. So I once gave testimony to the to the Colorado State Senate about climate change. And being a second born, I thought I'd just be annoying. And so I took a pen, and as I was speaking, I picked the pen up and I dropped it, picked the pen up and I dropped it. I kept doing that. And finally, one of the senators said, "What are you doing?" Right? I said, "I'm trying to demonstrate two important principles. Number one, that pen will never stop in midair. Gravity is gravity. How many of you have woken up on like a Monday morning, plastered to the ceiling of your bedroom going, oh darn, it's another low gravity day? Right? Doesn't happen. Right? That's a fixed, unbreakable law, gravity. The other thing I was demonstrating there was free will. I can stop doing that. I can stop doing that. Right? And that's the difference, really. So on this planet, you can have free will, but you don't, but there's a limit to it, right? So we don't like limits. We're hard to predict. And yet here we are, the dominant species on the planet. And the planet is telling us, no, this is the way things are going to work. If you put greenhouse gases in the atmosphere, and I'll talk about that in a second, you will change climate. You don't get a choice in that. That's how the planet functions. So physics and chemistry work all the time. That's actually a good thing, right? So imagine if you got on an airplane and you didn't quite know what the gravity was going to be, or maybe it would vary, right? You wouldn't be flying, right? So this is, to have these fixed unbreakable laws is really important. It also provides a lot of predictability. So we can, for example, we know that I use an example here. So sulfur's in coal. It's a mineral pyrite. When you burn coal, you get sulfur dioxide. Sulfur dioxide will react with water in the atmosphere and make sulfuric acid. So while we knew that basic chemistry, and we knew that acid rain, for example, was a thing and it was going to happen, it took us a long time to say, hey, we got to do something about scrubbing SO2 out of smokestacks. But therein lies the fundamental issue. We did not want to have to deal with the sulfur in coal, so we kind of ignored it. That didn't stop the acid rain, but it eventually made it bad enough that at some point we had to do something about it. All right, so I'm going to challenge you with this, and you can ponder this and debate it in your head. Is it possible for a species that loves free will as much as we do to live on a planet that says, nope, you've got to obey the rules? By the way, I would ask people frequently when I gave talks, how many people have ever come up to a stop sign and not come to a complete stop? Raise your hand. If you've not come to a complete stop. How many people come up to a stop sign and rolled through it? All right. Yeah, you know that's illegal, right? The planet doesn't give you that choice. The planet will tell you, nope, you have to obey the law. But we, when we make the laws, we can break them. All right. Okay. Global climate. So climate is actually pretty simple on a global scale. It's more complicated on the local scale for a variety of reasons, but it's pretty simple on the global scale. So you can calculate the average temperature of our planet quite simply and easily if you know three things. How much energy we get from the sun. We're basically a sun-driven planet. There's a little bit of radioactive energy coming out of the planet, but the sun is where we get our energy. Right? The second thing you need to know, so the only thing you need to know about the sun is how hot is the sun and how far away are we. Those two things physicists figured out about 150 years ago, how much energy we get, and so what our temperature should be. How much of that energy is reflected back to outer space by clouds, ice particles, etc. That's called the albedo, or the reflectivity of the planet. So if you know the reflectivity of the planet, you can estimate it. You know how much energy is coming in, how much is bouncing off and going back to outer space. You know those two things. The third thing you need to know is the amount of gases in the atmosphere that we call greenhouse gases that absorb not the sun's energy, they absorb the Earth's energy. So when the energy comes in, strikes the planet, warms it up, we all know this, asphalt gets hot, the Earth begins to radiate energy back to outer space. If there's something in the atmosphere that can absorb that energy, and that's the greenhouse gases, then it will increase the amount of energy in the atmosphere. All right? That's the simple physics of greenhouse gases. And so any gas that you put in the atmosphere that absorbs in the infrared, which is the frequency that the Earth radiates to outer space in, is a greenhouse gas. The number one greenhouse gas, by far, water vapor. Second one, carbon dioxide, methane, etc. All right. As I said, we can calculate the temperature of our planet, and we have done that. The Earth's temperature without greenhouse gases is about negative 18 degrees Celsius, negative 18, so 18 degrees below 0 Celsius. Clearly, I think too cold for advanced life. We'd be a frozen planet if that was the case. The Earth's temperature with greenhouse gases, however, so if we put satellites up in space, if we put a whole lot of thermometers down on where we are, we can calculate the average temperature of the planet. That comes out more like to plus 15 degrees. So the difference between plus 15 and negative 18, which is 33 degrees C, it's about 6 degrees Fahrenheit, that's because of greenhouse gases. That's and so greenhouse gases actually make the planet habitable. They take us from a frozen thing to something that is a very nice place to live on. By the way, the more you study the planet, the more you think this is a pretty amazing place. All right, so if we add lots of greenhouse gases to the atmosphere, and we have, there will be more energy in the atmosphere, and by definition, climate will change. So this is a physical law limitation. I've been asked frequently, do you believe in climate change? And I say, I don't get to believe. It is a physical thing, right? So if you believe or not in climate, the planet could care less whether or not you believe in climate change or not. The planet's just going to say it's going to, climate change is a thing. You've got to learn to live with it. Okay. So a few observations about climate change. Timing is an important thing. You live on a water planet. So 70% of the Earth's surface is water. Oceans are deep in many, many places. It takes water a long time to heat up. It takes water a long time to cool off. So if we add greenhouse gases to the atmosphere, we raise the energy in the atmosphere. About half that energy is expressed as temperature, as heat. The atmosphere warms up. Almost all of that warmth that's happened so far has been going into warming the ocean, because the ocean has what we call large amounts of heat capacity. So for example, so I show a pot up there. I used to tell students, don't do this. It's a thought experiment. You put two pots on the stove. You put a cup of water in one. You put no water in the other. You turn the heat on exactly the same as much as you can. Go away for about 2-3 minutes. Don't need much longer. Come back. Put your finger in the water. It's barely warm. All right. Now, again, thought experiment. You take your finger, you put it in the other pot, and the sizzling sound you hear is the end of your finger burning. Right? Same amount of energy went into both pots, but the water is barely warmed up. And why is that? Because water has a lot of heat capacity. Right? So it takes water a long time to warm up, takes it a long time to cool off, which translates on our planet into the fact that what we do to the planet, our kids have to deal with. And what they do to the planet, grandkids have to deal with. So there's always an intergenerational issue when it comes to climate on our planet. And that's just because you live on a water planet. If there were no oceans on the surface of the planet, hopefully just enough fresh water for us to live on, you would have a different planet. The planet would respond much faster. For the amount of CO2 we put in the atmosphere already, it would be a much warmer planet. Right? It's just not that warm because it takes oceans a long time to warm up. This leads to this is my quote on the right, until one generation is willing to forego short-term gains for the long-term benefit of its children, we won't be able to address climate change. And that's just a fundamental ethical challenge that we have right now. The picture is of my granddaughter, Amelia Louise. That's baby upside down. She's 11 now. She doesn't look like that anymore. She's still cute, but she doesn't look like that anymore. I show this picture because as a proud grandfather, I'm concerned. And as I get older, and as I watch my kids and my grandkids grow up, this is the intergenerational issue is the one that begins to get to me the most. I don't want to leave this planet in worse shape than when I found it. And right now, although it's not up to me, it's up to us. Right now, that's not happening. All right. Large changes happening now. So what you're looking at is a movie, or a movie, it's a kind of a movie. Anyway, that's sea ice up in the Arctic. And the whiter it is, the thicker it is, right? So the very white stuff is 4-year, it's been out there for 4 years. There's sea ice there, the lighter color is the younger sea ice. And when we started up, the whole Arctic was covered with the white stuff. So the thick sea ice, it's important. Thick sea ice can survive a warm year, 2 years, a warm 3 or 4 years even, right? As time goes by, what you're going to see is the thick ice is going to go away. So what's been happening in the Arctic is it's warming up, the ice is melting, and the initial impact is for the thick ice to get thinner and thinner and thinner. You'll also notice that the ice spins off around the east side of Greenland and goes down there. Those are the icebergs, by the way, that flow out into the Atlantic Ocean and sink the Titanic and make Leo DiCaprio famous. So, but what you see here is 2011. As time goes by, it only goes to 2016, by the way. By the time you get to about 2013, 2011 or so, almost all of the thick sea ice is gone. And you're in a situation in which you have ice. You still have ice in the wintertime in the Arctic, but it's 1-year ice. It's thin ice. 1-year ice can go away. Google Lake Michigan or Lake Superior back in the 1960s when they would freeze over pretty much every winter. Or Erie, Lake Erie's an easy one, would freeze over every winter. No longer freeze over. But freeze over, the lakes would melt out over a matter of maybe 2 weeks or something like that. As the water gets warm enough, as the wind starts to blow, the ice churns, and these big areas of ice would go away pretty rapidly. That's the situation we're in right now with Arctic sea ice. Now, why am I showing you Arctic sea ice? If you remember, 3 things that drive climate. One of them is reflectivity. So when you've got summer sun coming in here 24 hours a day in the Arctic, if that's covered with white ice, that energy is reflected back to outer space. That's what keeps the Arctic cold. If you've got blue water, you've got the opposite situation. You got energy that blue water can absorb energy. And so you'll go from totally reflective to almost totally absorbing energy in a pretty short period of time. And that's something that I keep my eye on, and I would encourage you to keep your eye on as well. The impacts are not all local. What happens elsewhere will matter to everyone's economy. We're all tied together. That's just a reality of how we live on this planet. Food costs will increase for all. Climate refugees are probably my biggest worry when it comes to climate change. Because about most of the population of this planet lives close to the coast. And as sea level rises, and we'll talk about that in a minute, they've got to find a new place to live, and it's not like we've got another planet. They've got to find some place to live. And it's not like other countries are going to open their arms and go, okay, come on in. All right? So we're going to all pay a lot for sea level rise in the end, but it's slow, and it's going to take a while, but it's going to cost a lot. All right. What you need to know about sea level rise in about 4 slides. First of all, there's a very, very, very good relationship on our planet between the amount of greenhouse gases, the temperature, and the sea level. All right, this is your planet going back from today, roughly back 800,000 years. This is from an Antarctic ice core. I do ice core research, so this is some of the stuff that I work on. But you see what we call interglacial periods, glacial periods, and et cetera, et cetera. What you see is a very good relationship between how much CO2 is in the atmosphere, the temperature of the planet, and sea level. Okay? Now, what I'm going to challenge you to think about here in a moment is scale. Right? How much is temperature changing? How much is sea level changing? Right? And that you can see most easily on a graph here where we have global mean temperature and we have sea level. This is the only graph I'm going to show you, by the way, class. So today, the global mean temperature is about 15 degrees. We saw that earlier. If you go back 20,000 years ago when the planet was, ice sheets were covering Canada, covering Fennoscandinavia as a glacial period, it was about 6 degrees colder at that time. Right? If you go way back in time, about 40 million years ago, when the planet was much warmer, it was about 4 degrees warmer at that time. So this gives you a scale of temperature change. So there's about a 10-degree temperature change from +4 relative to today to -6 relative to today. That's what we call the dynamic range of temperature on our planet. Now compare that to the dynamic range of sea level, right? So 40 million years ago, when it was 4 degrees warmer, sea level was about 80 meters higher. Meters. Multiply by 3. 20,000 years ago, at the peak of the glacial period, sea level was about 120 meters lower. So 10 degrees in temperature on our planet translate into 200 meters of sea level change. That's roughly 600 feet. I'll pause for that to sink in for a second. All right? That's a lot. So the most dynamic climate variable on our planet is not temperature, it's sea level change. Right? That's an important consideration. It's an important consideration because keep in mind that, for example, we've already had 1 degree of temperature change. We're arguing about whether or not 2 is a good stopping place. And if for 10 degrees is 200 meters, that means roughly, if it's not linear, but roughly for every degree it's about 20 meters. It takes time to melt ice, remember. So we've already baked in probably in the neighborhood of 10 meters, if not more, of sea level change. Right? What would I'm going to show you what this looks like in maps. But that tells you what we call the commitment, the climate commitment that we've already have right now. Oops. So for years I was part of a team of scientists that met with TV meteorologists, and I talked to them about climate change. And one of the TV meteorologists in Miami had me go live to Miami in the morning, and he asked me on camera what I thought about Miami's future. And I said this. I said, the coasts are toast. And I got a few comments about that. Anyway, sea level rise will be slow, but it will be steady. So expect some thresholds. And not all the thresholds, by the way, are climate thresholds. Most of the thresholds are actually human thresholds. So when an insurance is unavailable, that's a threshold. When the gas lines have to be replaced, when the roads have to be replaced, these are thresholds as well. All right, so what does about 13 meters of sea level look like? This is Bangladesh. You see that I pulled this one out because there's very little left of Bangladesh. There are millions and millions of people in Bangladesh who have to go somewhere. And the countries to the east and west of them aren't really opening their arms up and saying, come on in. So this leads to the climate refugee issue. This is about 20 meters of sea level rise. You see the Gulf Coast. This breaks my heart because I am a huge fan of the food that is served down here in New Orleans and Thibodeau. And I find it really depressing to think that that culture could be underwater. Note that southern Florida with 20 meters of sea level rise. So Miami, the folks I was talking to. By the way, Miami was a swamp 100 years ago. And Miami will be a swamp again at some point down the road. Anyway, note that the tip end of Florida here is under 20 meters is pretty much gone. What's really important about right here in Orlando? Disney World, all right? Does Disney World survive 20 meters of sea level rise? Yes, okay? As a matter of fact, you can sail the Disney Princess right up to the Magic Kingdom, all right? You gotta take the good with the bad, folks, all right? Okay, so this is a little test here. This is called the Delmarva Peninsula up east. What is this state right here? Delaware. What was the first state of the Union? It's on the license plate. Delaware. So you can remember what I call long-term climate change. You can remember long-term climate change if you can remember this. First in, first out, okay? If you can remember FIFO, you can remember long-term climate change. We're not going to be electing senators from a salt marsh, all right? So at some point, Delaware's gone. Well, maybe we'll do something. All right, I'm about done here. Have we been depressed yet? Okay, we'll raise this up here in a minute. I'm going to end on a high note. All right, I want to talk about the importance of communication. And it's important that we find ways to communicate this in a way that engages people. I've tried to occasionally throw in a little bit of humor here to try to keep you engaged in this, because I can, as a scientist, just sit here and terrorize you. And that's not going to do anybody any good. So this is an example of this. This is a screenshot off a computer, my computer actually, from a place called dogsports.com. Dogsports.com is the official website for the University of Georgia football fan, okay? Dogsports.com. So here's dogsports.com. This is a little thing, this is several years ago, and this is off them. The USGS, U.S. Geological Survey, predicts that if ice caps were to melt completely, sea level would rise by approximately 80 meters. That's an A+, right? If we can get polar ice caps to melt only halfway, sea level will rise 40 meters and the face of the Earth will change forever. This is 40 meters of sea level rise. This is their interpretation. Why? Because they don't like Gainesville, they don't like the University of Florida, right? So if you can find that place where you can engage somebody, you can engage the average Florida football fan if you can get them to understand sea level rise just might wipe out Gainesville, okay? Whoops, and then it ends down here. Now's the time, Georgia fans. Trade in those efficient vehicles for a gas guzzler, spray some aerosol, burn as much coal as possible. We can make Florida a thing of the past. By the way, spray some aerosol is wrong, but you know what? Overall, it's an A, all right? Okay. All right, so what do we need to do? All right, I'm going to give you three things to ponder here. Number one, show the kids some love. You live on a water planet. The impacts come after the causes by 50 years or more. The more that we can think about future generations, the easier it's going to be for us to tackle climate change. So first thing to do is show the kids some love. All right? Second thing, show the poorest of the world some love. Everyone must care about our shared atmosphere and a shared planet. It doesn't matter if this country and the industrialized countries of the world stop burning fossil fuels if they're still burned in Africa, if they're still burned in the poorest parts of the world. About 2 billion people live on this planet in poverty so deep that the health and the environment cannot be a consideration to them because they can't afford to make that judgment. Right? So you got to figure out a way that we as human beings can embrace us as a collective species in order for us to address this. Right? So show the poorest of the world some love, bring them along, and that will help us deal with climate change. And third, population must be controlled. All right? The best and most lasting way to deal with population is to empower women, economically and politically. We see this over and over. You take a course on demographics and population, and you will find this is the case. It is time to end male domination. I don't know who invented that. I benefited from it, but I didn't invent it. But this is, if you look at where population growth is, it's places where women have less power and less power both politically and economically. And we have to control the number of people we have on the planet. So I've given you three things. Show the kids some love, show the poorest of the world some love, and let's show each other, from a gender point of view, some love, all right? I think those are positive things. I think those are things that help us as a species grow as a species, adapt as a species, be a better species. So ironically and interestingly, in order to address climate change, we've got to be better. We've just got to grow up as a species, so to speak, and be better. All right, one last thing I want to tell you. Whoops. Oh, man. I don't know how to get this back. I'll just put the slide up, my last slide. It's an unabashed, as the Dean of the College of Arts and Sciences, I have to show you this slide. It's in my contract. I've shown you a lot of science today, but the solutions require understanding humans. We need a blend of the humanities, the social sciences, and STEM to understand and address today's environmental problems. When I started out lecturing on climate change, it was all about science, because I'm a scientist. But I learned early on this is really about human beings and the importance of the humanities, the importance of the arts, the importance of social studies. So get that liberal arts degree, kids, and help us solve these problems. Happy to take questions. Happy to have arguments. I've said nothing controversial here, so there's no way there's a question. Yes, sir. Yes, they are taking it to heart. I wouldn't say all of them are. I would say that more of them are taking it to heart than certainly when I was in school. I mean, I don't know if you know this, but we're being sued, you and me, by our kids. I have no idea how they're going to collect that, but they're suing us. Yeah, I have found that over time, the students in class, I mean, they grow up with this. They understand this innately. And frankly, it can be a bit overwhelming, right? It can lead them to, despair, basically. And if you talk to kids today, more and more of them will tell you, I don't want to have kids, because I don't know what I want to bring kids into this world. And if you want to kill off a species, one of the most effective things to do is not have any more of us. So this is something we have to come to grips with. We have to understand our kids and how they're dealing with this. Sir, I can see a question formulating here.
While we're talking about crystal balls,
yeah.
has anyone looked into the sociological consequences of rising sea level? Right now we've got all these people spread out to some degree.
Yeah.
You start to squish, the colors go dry land, you start squishing them closer and closer. Temperatures will run tighter.
Yeah.
And there's all be all kinds of reactions.
Yes. So what you're talking about is, so if you look at it doesn't take, you don't have to be Nostradamus to say, look, as sea level rises and land shrinks, there's a number of things that are going to happen. One is a lot more tension, a lot more struggle to own that last little bit of land. And then they got to move. And then struggle number two comes because where are they going to move? There are some Pacific islands that have already made deals with Australia and New Zealand that they can move there. But the big problem comes in Asia. It comes in coastal communities around North America and other places that those folks have got to go somewhere. And we don't have a place for them to go. Do you have your hand up? Yeah.
Is there a map of the global situation that shows Florida and Bangladesh?
Yeah.
But it shows the whole world as to what areas will no longer be land masses?
Yeah, fortunately, so this is, I chuckle about this, but every now and then there's something good on the web, right? And there are a couple of websites you can go to that will show you, you can just type in 1 meter sea level rise, 2 meters of sea level rise, or 1 foot, 5 feet, whatever. And it'll show you what that looks like. We've mapped, particularly in North America, we've mapped the coastal regions pretty well from an elevation point of view, so it's actually pretty detailed, what you can see. I did not show North Carolina. I didn't have a map easily available, and plus it's depressing. I find it deeply ironic that the memorial to the Wright brothers will eventually be underwater. Yeah, out on the Outer Banks. That bothers me. I'd love to stop this. Yeah. Yeah. Go ahead. The Arctic is melting faster because it's warmer up in Greenland than it is down in Antarctica. Antarctica is a chunk of ice right at the South Pole, surrounded by ocean. It's isolated, and it gets ridiculously cold there. Greenland, it gets cold. I've done ice core work in Greenland at -40, so it's not, but Antarctica gets -60, -70. So the answer to your question is it's a little bit warmer in Greenland, so Greenland's actually, now the good news is there's less ice in Greenland than there is in Antarctica. Most of that 80 meters eventually comes from Antarctica. Second question.
So everybody drives cars now.
Yeah.
For the most part. So what are the most environmentally friendly cars?
It's a great question. All in all, electric cars would be, but you got to make the electricity from some method that doesn't itself burn fossil fuels. So, you know, solar, wind, et cetera, if you pair those things up and you really decrease the amount of greenhouse gas emissions that you make. But there are other forms of propulsion that people are using now, hydrogen, which you can make from water. There's a number of, some vehicles. Also, you can make natural gas naturally, and that can be burned in automobiles as well. Yeah, I heard that. Yeah.
You mentioned at the end of your presentation that population control is a meaningful way of mitigating this
Yes.
long term.
Yeah.
What might you say in response to economists who identify fertility rate declines in countries like South Korea and the United States as being an imminent problem? So how do we square these two issues of decline and overpopulation?
Excellent. Excellent. You get an A for critical thinking. A for critical thinking. Yes, there is a fundamental problem here. And if you dig into it a little bit, you find that you don't necessarily have to add people to the planet to grow the economy. You can grow the economy itself. So you can grow consumption in that way. It doesn't grow as fast as if you grow the numbers of people. But there's a limit to the number of people you can put on the planet. So growth in itself is not, the ultimate goal here. The ultimate goal is to live sustainably on the planet. And you need to find some way to make that equation work. But yes, I mean, right now we are in a situation where economists will tell us, we're worried because people are having fewer kids. That means, we'll have struggle with economic growth in the future. Also, the way that we manage our societies, it's a problem as well, because if you've got a bunch of folks who are retired and need money from Social Security, and you have fewer people paying into Social Security, so there's a whole bunch of short-term problems that go along with that. But eventually, we've got to figure out a way in which we can live sustainably on the planet, which will mean a different calculation for how we calculate wealth on the planet. Mm-hmm. Yeah. Oh, no. Yes, you can. Where's money come into play with this? It's all over the place. When I talk to you about lead, when I talk to you about those things, it was money, right? It was the lead industry that didn't want to get the lead out, so to speak. How about that? A joke. Yes, I mean, particularly if you go back into the late 1990s, early 2000s, there was a lot of very behind-the-scenes pushback on the part of the fossil fuel industry to change the narrative. Right? I would not expect otherwise. They're making a lot of money off of this. Now, does that mean that the fossil fuel industry is evil? No. I will tell you no. We need energy. Right now, if you were to say we're going to stop burning fossil fuels today, that would collapse our economy. That would collapse our societies. We cannot afford to do that. We have to be smarter about how we move from one type of energy to another type of energy. And we have to respect the fact that the type of energy we have now, it's, you know, the infrastructure's baked in. So while there are people who are trying to move more slowly, even those people, I think, understand that at some point we're going to have to move to a different form of energy. But we need to do it in a thoughtful way. Yes, we need to do it already. I get asked every now and then, whose fault is this? And I don't like to ascribe fault, but if I had to point the finger at any one group of people, it would be the politicians who have not done enough to understand the problem, and then they're our elected representatives. They should be saying, all right, folks, we got to deal with this. I know it's hard to work with, I know it's hard to deal with, but we've got to deal with this. And I think that that's in a democracy, that's how it should work. Did that kill all conversation right there? Yeah. Yeah. Yeah, sure. Sure. We've already slowed it down. We have slowed, I'm sorry, I cut you off. What was that? Okay. We have slowed it down. So we've moved away from coal, which is a very carbon-intensive fuel, and one that we have a lot of. If we burned all the coal, we could do this. We could really do this thing. We've moved away from coal towards natural gas. Natural gas, we get more energy, less carbon dioxide, because natural gas is a carbon and 4 hydrogens. So when you burn it, you not only get CO2, you get H2O, you get water vapor. So part of that energy that's released is making water vapor, which eventually falls out of the sky as rain. So we've slowed down our release in this country. We've slowed down our release of carbon dioxide by shifting from coal towards natural gas. That's a good thing. We should do that. But I think we should be more purposely taking advantage of the fact that we've got natural gas in order to bridge today's situation to something down the road. Is there another question lurking in here?
I'm just thinking about the average household. What people can do. There are many things that people do. And a lot of people do believe in crisis. Some people don't.
Yeah.
But it just seems to me that if we could be well informed and convinced, something done today, we could make a difference.
I agree. And so there's a lot of things I could tell you about having a more fuel-efficient car, fix the windows, you know. In your house, it's windows and the doors where most of the heat goes out or in, depending on the season. But by far the most important thing that you can do is to take it seriously and vote based on your convictions, by far. And so I think when we as a people stand up and say, we're done, we got to deal with this, I'm tired of electing people who ignore this problem, then things will change. Hopefully things will change. Any other questions?
You haven't mentioned atomic energy.
Yeah.
Would that be a great help?
Atomic energy, yes, it can be. Atomic energy is all right, so anything that doesn't produce greenhouse gases is better than something that produces greenhouse gases from a climate point of view. All right? The current way in which we generate electricity from nuclear energy has a downside in that it produces nuclear waste. And in the same way that fossil fuels produce CO2, which is a waste you have to calculate and deal with, if you talk to the economists, it's sort of a full circle kind of economic model. Nuclear waste is also expensive. We don't have enough places to put it away right now, and we have no history with how you manage something over 6,000 or 7,000, 8,000 years, right? So we don't. Now, having said all that, there are new generations of nuclear reactors that are coming online that produce less waste. They're smaller. They're, you know, in some community, they're actually located in the community. They can be very safe. So I don't think that nuclear energy is something that we should discount. It is a bridge fuel. So the amount of fissionable material, the uranium-235 that you need to actually make it happen, that's not in huge abundance on the planet either. So if we went whole hog on nuclear energy, we could run out of fuel for nuclear energy in a generation. So it's a bridge, but it's not a long-term. The long-term energy for the planet is the sun. That's where the energy comes from.
You had to hazard a guess.
Mm-hmm.
How many years would it be before Miami and New York City become unhabitable?
Miami sooner than you would think, probably in the next, easily within the next 50, 70 years, something like that. And I was just down in Miami the other day. If you've not been down there recently, they are building high rises right on the coast, right and left. I mean, wow, I hope they get the money back out of this. Anyway, and the reason why I say that is Miami's built on porous coral rock. And so you can't build a dike around Miami because the water will just go underground and come up from below. Manhattan is already planning to build a dike around Manhattan. And in a full circle of history, they went to Holland to figure out what the best way to do this. So for his history buffs, it was New Amsterdam to begin with. So anyway, probably a bit longer because of that. But at some point, you know, you can actually have some fun with this, thinking about it. As sea level rises in Manhattan, would we go to a model in which it becomes sort of like Venice? You take the infrastructure off the basement and you move it up to the roof, and then you get around by boat. I mean, we've got so much invested in the buildings in Manhattan. I think it'd be kind of crazy to get rid of them. That same thing might happen in Miami, but it's harder to deal with there because you don't really have any dry land to deal with. One of the things I hope we do, which is something we do here in Carolina, although we need to do it better, is we need to remove all the nasty stuff out of the buildings before they get inundated or destroyed. Asbestos, oil, all the, household cleaners, all that kind of stuff. We have to be thinking about how do we clean up before we let the ocean come in. Look, this is not intended to be really depressing, okay? We are, as a species goes, extraordinarily clever. We are extraordinarily adaptable. Look at where we are now. Look where we were 200 years ago in this country. Right? Look where we are now. And frankly, back to, shout out to the women, we did that with one arm tied behind our back, right? So we did not allow women to really participate in that whole process. This is a problem we can face. This is a problem we can deal with. But like everything else, step number one, admit you got a problem, and then move forward. I am an absolute solid believer in the ability of human beings to tackle any problem that comes our way. We just have to have the willingness to do it. Okay? Thank you so much for listening.